Howdy, it's Miss Kosh. I want to talk to you about transformation of graphs. I am assuming that you have seen this before, okay? So I'm going to teach it like you've never seen it, but teach it faster because I think that you have seen this in Algebra 2 and possibly even Algebra 1. Okay, so there's a few things that we're going to look at on this. We're going to say that our transformed function, this g of x, would have been f of x and then stuff happened to it. Okay, so f of x would be our parent function like x squared, or f of x is equal to the absolute value of x, or we can come up with all sorts of different initial parent functions, and then we're going to start doing some transformations. So there are what we call rigid transformations versus non-rigid transformations. Okay, so a rigid transformation, basically the idea is I take a graph and then, let's see if this will work for me, and then I just kind of move this around, okay? So I can take this, I can move it here and there. Notice how this parabola, lovely little thing here, and I could reflect it. Well, okay, I forget how to use Notability. Okay, I mean, I could reflect it. Notice that its shape didn't change. So all of these, and then I'm shifting it anywhere and everywhere I want, up, down, left, right, whatever. All of those would be rigid transformations. So a non-rigid transformation would be where the shape changes in some capacity. So it's been stretched one way or the other. A vertical shift is when you add something at the end of your function. So like if I had y is equal to x squared plus 2, it's going to shift the graph up 2 units. A horizontal shift is where, or I'm saying y equals, this could have been f of x, or in our case here, we're talking about f of x was x squared, so then g of x is equal to x squared plus 2. Okay, whatever, something like that. A horizontal shift, let's use a new color, could be something like g of x is equal to x minus 2 quantity squared. Okay, and now this one is going to move it to the right 2 units. Okay, one way to think about that is that if this is x squared right here, y equals x squared, what we've done is now this thing will equal 0 at positive 2. And so it's going to do that sort of thing right here. So that's been shifted to the right 2 units. Notice it's the opposite. When it's inside here and it's a horizontal shift, it's going to be the opposite. If it's a plus, like if I have g of x is equal to x plus 1 cubed, that's actually moved it left 1. I think you typically show up in my pre-cal class knowing this. So hopefully that's the case this year also. If not, let me know and I'll clarify. Okay, so another rigid transformation is a reflection. So if I can reflect over the x or the y axis. So if I change, basically what happens here is if I have if f of x is, say, equal to x squared, and I want h of x to be equal to negative f of x, what that's saying, okay, that's equal to a negative x squared. So now, instead of having the original parent function like this, now we've taken every value that we get, and we've every y value we get, and we make it negative. Ooh, that's, come on, Notability, that's not what I wanted. Every y value then becomes negative, and it does. So this would be that h of x function down here. On this particular one, if let's say f of x is equal to, let's say it's equal to the square root of x, and then I want k of x, because k is our favorite letter, to be equal to f of negative x. Now what happens here is this would be equal to, well, anywhere I saw an x from above, up here, I'm going to have to plug in a negative x. This is the square root of negative x. What this has done is this has now changed our domain. Okay, the parent function here started like this, started at 0, 0, and then the square root of 1 is 1, the square root of 4 is 2, the square root of 9 is 3. So it would have the points 0, 0, it would have 1, 1, it would have the point when x is 4, the square root of that is 2, it would have the point 9, 3, and so forth. This one, however, if I've tried to plug in, if I say k of 4, well, that's equal to the square root of negative 4. That's a non-real value. Okay, so this is not in my domain, so it's going to be doing the opposite scenario, going something like that, where now you have to plug in negative x's because then they become a negative negative. Okay, so like what I'm looking at here is if I plug in a negative 4, then I have a negative negative, which becomes a positive, or you know what, maybe I should have written, let's write it here. This would be, oh, now there's my eraser, okay. If I plug in a negative 4, then a negative negative becomes a positive 4. The square root of positive 4 is equal to positive 2. So this would have been the point, negative 4. Okay, I had somebody walk in. I guess I need a note on my door. I'm going to try and figure out how to put those two videos together. Okay, so this would have been the point, negative 4, positive 2. So continuing on, that's a reflection. So when the negative is inside, it's going to be a reflection over the y-axis. So notice it had gone from here to here. Okay, the vertical stretch is typically easy for us to understand. If I have, if I've got the graph y is equal to x squared, and then I want, you know what, hang on, let me use f and g. F of x is equal to x squared, and say g of x is equal to 2f of x. This is just like saying 2 times x squared. What we've done is we've taken this and we've stretched everybody up a little bit this way. Okay, so I wish you could see my hands. Basically what I'm doing is I'm pulling it away from the x-axis. Okay, so that's a vertical stretch. What I like to do is when this a value is bigger than 1, I refer to it as a stretch. Okay, so say when a is 2, it's a vertical stretch of 2. If a is 10, it's a vertical stretch of 10. When a is between 0 and 1, then I would say, so say like a is equal to 1/2. To say that that's going to take this original parent function here and actually kind of flatten it out a little bit. That's a little confusing, but there goes that. What I would say, it's correct to say it's a stretch, a vertical stretch of 1/2, but that doesn't make sense intuitively. So I would typically say it's a compression of 2. Okay, so I stick to the language of a stretch when it's bigger than 1 for the this vertical stretch, and then I switch over when it's something between 0 and 1. I switch over and say this because the compression idea, because that makes sense. Compression tells me I've pushed down from the top and it's getting fatter. Okay. However, if we look at, it works differently when we look at the horizontal stretch or shrink, and so with something like that, a horizontal stretch or shrink is going to push things in or pull things out horizontally, okay? And so then what happens here, let's say f of x is equal to x squared, and let's say g of x is equal to f of 3x. Okay, so what that means is I've taken out my x value and I've plugged in 3x, and this would clean up to be 9x squared if we want to think of it in that way. This right here is a vertical stretch of 9, but I wasn't given that initially. I was given this right here, and so what this is this is a horizontal. It's a horizontal, well, let's talk about that. What that's going to do is it's going to take our parent function and it's going to make it a whole lot skinnier. Okay, so it's moved this guy in horizontally. So I like to think of this as a horizontal compression, a horizontal compression by a factor of 3. Okay, you could also call that a stretch, a horizontal stretch of 1/3. But when I talk about a stretch of a number less than 1, doesn't make sense to me intuitively. So we'll keep talking about this. We'll keep practicing this. If it had been this, say h of x is equal to f of 1/2 x. What this would do, this would be like 1/2 x squared. which is also 1/4 x squared. This becomes, it's taking my parent function and moving this parent function, making it go wider. So this would be a horizontal stretch of 2. Okay, which is what we refer to in here. It's a shrink or a compression when it's bigger than 1, and it's a stretch when it's between 0 and 1. Okay, last thing that they point out here, and I am about to have to go and get on a Zoom call with people. It says, as a reminder, factor out B to determine C. So if I have something like this, f of, or I don't know, I'm trying to be consistent with my notation and I keep failing. Okay, so say g of x is equal to the absolute value. I think this one is the next one on your 3x minus 6. Okay, I can't say that this is a shift of 6 because what I need to do first is I need to take this and say, okay, this is 3 times x minus 2. So this becomes a shift of 2 units to the right as opposed to 6. So always, always, always factor out that b value before you try and figure out what your shift is doing. All right. I already have videos for those 5 examples, so work through those. If you have questions and need clarification, please let me know. Good luck. Go practice.